Welcome to the deep dive. Today we're wading into, well, frankly, one of the most stressful investment decisions in high-precision manufacturing. We are talking about wire electrical discharge machining, specifically comparing the MS-WEDM, that's your reliable, cost-effective workhorse, against the LS-WEDM, the ultra-precision beast that requires, as our sources rightly put it, a terrifying investment.
It really is a significant leap financially and technologically.
Right. So our mission today, for you, the listener, is to cut through that sticker shock. We want to build a clear, objective checklist to help you figure out exactly when the technical demands of a job absolutely justify sinking that huge capital into the low-speed machine.
Exactly, because it's not just about, buying a fancier model. These are fundamentally different tools with different operating philosophies. Think of them as two different financial instruments, really, for achieving very different goals. Your MS-WEDM, the medium speed, that's usually the profitability champion, right? It delivers excellent parts, great quality, standard industrial precision, typically around plus or minus 0.003 millimeters. Good enough for most things.
Okay.
But the LS-WEDM, the low-speed system, that's in a different league. It's reserved almost exclusively for those absolutely mission-critical parts. It demands, and crucially, it achieves, the absolute pinnacle of accuracy. We're talking tolerances down to plus or minus 0.001 millimeter.
Wow. Okay. That jumped from 0.000 to 0.0001. That sounds small, but in manufacturing terms, it's huge.
It's massive, and understanding why you'd need that jump is key to making the right investment.
Okay, let's unpack that then. Because when the stakes are this high, we really need to isolate the non-negotiable specs. What technical requirements, putting aside the obvious price tag for a moment, really define the need for that low-speed system? It feels like it all boils down to this almost obsessive pursuit of perfect finish and, well, accuracy.
That's spot on. The absolute defining line is accuracy. The moment you hit a job specification demanding true micron-level accuracy, that plus or minus 0.00001 millimeter, you're basically exiting the sweet spot for MS-WEDM.
So if the job can live with plus or minus 0.0003 millimeters,
Then you absolutely stay with medium speed. It keeps you cost competitive, no question. But there's another critical differentiator: surface finish. Your MS-WEDM delivers a great finish, really smooth, maybe around Ray 0.65 micrometers, perfectly acceptable for many applications. The LS-WEDM, though, becomes necessary when the specification demands a mirror-like surface. We're talking down to Ray 0.05 micrometers. And this isn't just about looking good. Often that ultra-smooth finish is critical for the part's function, maybe minimizing friction, preventing fatigue, that sort of thing.
Okay, that makes sense. Looking at pictures of the machines, the visual difference is pretty stark, too. The LS-WEDM always seems to operate with the workpiece completely submerged in fluid. It looks, well, complicated, and maybe high maintenance compared to the open-style systems you sometimes see. Why is that submerged cutting system so absolutely critical for hitting that sub-micron accuracy? Isn't EDM just about erosion? Don't you just need to flush the debris away?
Yeah, that's a great question. And what's fascinating here is that the submerged system is really the bedrock mechanically and chemically of the LS-WEDM's precision. It's about way more than just flushing. It's really about thermal mastery. Absolute control over temperature.
Thermal mastery. Okay.
Think about it like this. When you're cutting metal with EDM, every spark generates heat. It's tiny, yes, but significant at this scale. If you're chasing a dimension of plus or minus 1 micron, 0.001 millimeters, even a fraction of a degree change in the workpiece temperature can cause microscopic expansion or contraction. Imagine your part is, say, 100 millimeters long. That tiny bit of thermal expansion over a long cutting cycle, it can completely throw your tolerance out the window.
So it's like trying to draw a perfectly straight line on a piece of paper that's subtly warming up under a heat lamp. The material itself shifts just enough.
Exactly. It shifts just enough under your pen wire to ruin the job. That's precisely why the LS-WEDM uses temperature-controlled deionized water. That bath creates this perfectly stable thermal environment. It acts like a massive heat sink, instantly neutralizing the heat from every single spark. It stops those microscopic dimensional shifts that are absolutely non-negotiable in, say, aerospace or medical parts.
Right, okay. Total stability.
And our sources actually describe this submerged bath as a kind of trifecta for managing everything. It's that huge heat sink, yes. It's also an insulator, maintaining the part's dimensional integrity throughout the whole cut. And crucially, it's a vastly superior flushing medium. Because that deionized water is highly pressurized and constantly circulating around the cut zone, much better than just spraying fluid at it.
And I assume the superior flushing is key to getting that mirror finish you mentioned earlier.
Absolutely, 100%. To get down to that Ray 0.05 micrometer finish, the machine performs multiple very low-energy skim cuts at the end. Now, if even a tiny particle of debris from the earlier roughing cuts remains in that spark gap,
About
big trouble. It can interfere with the spark, it can cause a short circuit, or it can physically get dragged across the surface and mar that flawless finish you're trying to achieve. So that clean, constantly flowing, temperature-controlled deionized fluid ensures a perfect debris-free environment for that final critical pass.
Okay, that deep dive into thermal stability really does make the investment case much clearer, especially when accuracy is absolutely paramount. But let's shift gears slightly. From finish and stability to the actual complexity of the shape itself. What happens when a job demands really intricate internal geometries? Or maybe steep taper angles? Does the MS-WEDM start to struggle there too?
Yeah, and here's where it gets really interesting again, because that LS-WEDM engineering, it's obsessive about stability, not just thermally, but mechanically too. And that obsession gives it a vastly superior capability for handling complex geometry. It's built for it.
Okay, so when we talk about LS-WEDM advantages for geometry,
Yeah.
what are the specifics? What can it do that the medium speed often can't?
Well, we can probably break it down into three critical factors.
Yeah.
First off, wire control. The LS-WEDM uses incredibly advanced systems for constant wire tensioning and precise servo control. The goal is to completely eliminate wire jitter or vibration.
Okay.
That wire has to move in a perfectly straight, perfectly stable path. Think about cutting something complex like turbine blades or, highly specialized guys. You need total confidence in that wire path. Second big advantage, taper capability.
Now the angles.
Right. LS-WEDM offers high precision, independent control of both the upper and the lower wire guides. This lets you achieve incredibly steep and crucially accurate taper angles, sometimes up to 45 degrees.
45 degrees. That's seriously impressive for EDM.
It really is, and many high-tolerance parts, maybe specialized injection molds or extrusion dies, they absolutely rely on that ability to create sharp, steep relief angles.
Okay, so wire control, taper. What about getting into really tight spots, those tiny internal corners that are critical for things like stamping tools?
And that's the third point, and perhaps the most significant limitation for the MS-WEDM in complex parts. LS-WEDM systems are designed to run ultrafine disposable wires, sometimes as fine as 0.02 millimeters in diameter, just incredibly thin.
Wow.
And that thin wire allows it to machine extremely sharp internal corners. You can get near-zero radii that a thicker reusable wire simply can't physically negotiate. Think about microfluidic channels in medical devices or super fine tooling inserts. LS-WEDM is often the only way to make those features accurately.
Okay, so LS-WEDM clearly has the edge in thermal stability, finish quality, corner access, taper capability. It sounds like the superior machine hands down. Which brings us back to the elephant in the room, the money. Why wouldn't you just buy it every time? We have to address the financial reality. Yes, the purchase price is high, but as you hinted, it's those hidden costs, the continuous consumables. That's what can truly sink a shop if they choose the wrong system for their work. So let's talk brass tacks. The wire system. You said it's a huge part of the cost.
It absolutely is. This is a critical junction for your business model, for the listener trying to decide. Our sources consistently indicate that the wire system alone can account for up to 50%, 50% of the total operational costs of an LS-WEDM machine over its life.
50%.
Yeah.
Just for the wire and related parts. That's staggering.
It is. It's the single biggest trade-off you make when choosing low speed.
But, okay, let's flip that. If MS-WEDM uses this low-cost, reusable wire, what's the catch? What's the operational risk hiding on the cheap side of the equation? Surely there's a trade-off for reusing that wire over and over.
Absolutely there is. And that's the subtlety that many purchasers miss initially. The MS-WEDM typically uses molybdenum wire. It's chosen specifically for its strength and its ability to withstand repeated use, moving back and forth. That reciprocation is what makes it incredibly cost-effective per hour.
Right.
However, that very reusability and reciprocation are the sources of its inherent limitations, and yeah, its hidden costs too. That molybdenum wire wears down, it doesn't maintain a perfectly consistent diameter over time. And the constant back and forth motion inherently introduces vibration and instability, that wire jitter we talked about.
Oh, okay. So the very thing that makes it cheap also limits its ultimate precision.
Exactly. The trade-off for low wire costs is potentially increase downtime for checking wire alignment, replacing more sections of the spool, and ultimately lower confidence in holding that absolute tightest tolerance over a long, complex cut. You might have more setup time, more checks.
Got it. So the LS-WEDM avoids all those wear and jitter problems by simply scrapping the wire after one pass. That's the disposable wire principle you mentioned.
Precisely. The LS-WEDM generally uses copper or brass-based wire. These are chosen for their superior electrical conductivity, which is actually vital for those low-energy skim cuts needed for the mirror finish. And to guarantee absolute uncompromised precision, it uses a brand new section of this wire for every single millimeter of the cut. It moves unidirectionally, just one direction, usually at very slow speed, less than zero point 0.2 meters per second, and then it's chopped off and collected for recycling. It's disposable.
So you're essentially sacrificing that continuous wire cost for a guaranteed, virgin, high-conductivity cutting edge on every single micron of the path.
That's the philosophy. Guaranteed precision, but at a continuous cost.
Okay, we've established the huge difference in wire cost and philosophy. But you also mentioned other continuous costs for the LS-WEDM. What about the dielectric system, the fluid?
Right. Because the LS-WEDM is operating at such a high level, for this high-purity submicron work, its whole dielectric fluid system is far more complex and, yes, expensive to maintain compared to the standard filters and fluids used in an MS-WEDM. Well, we're talking about the continuous replacement of very high-purity filters, and crucially, deionizing resin beds. The quality of that deionized water, its electrical resistance, essentially has to be meticulously maintained within very tight parameters. This ensures the electrical discharge, the spark itself, is perfectly controlled for those fine finishes and tight tolerances.
So more consumables.
Definitely. These non-wire consumables, the filters, the resin, they add significantly to the continuous expense profile of the low-speed system. It's this interesting balance, isn't it? The MS-WEDM generally has a higher raw cutting speed and much lower consumable costs per hour. But the LS-WEDM achieves a level of quality that often prevents incredibly expensive rework or scrap, especially in high-stakes parts for aerospace or medical. Sometimes getting it perfect the first time is cheaper overall.
That makes perfect sense. This has been a really comprehensive breakdown covering the technical differences and those crucial operational costs. So, for you, the listener, we really need to boil this all down now into a clear, actionable investment checklist. You're standing there, maybe looking at the quote, contemplating the purchase order. How do you justify that massive LS-WEDM expenditure? How do you know it's the right call?
And it really has to be about the application meeting the margin. That's the core calculation. You absolutely must verify that your current work or realistic projected work requires the unique capabilities of the LS-WEDM, full stop. And just as importantly, you need confidence that your customers are willing to pay the necessary premium for that level of work, a premium that fully absorbs that high continuous operating cost we've been talking about.
Okay, let's walk through the 4 key questions now, the justification checklist.
All right, question 1, tolerance. Is the standard plus or minus 0.003 millimeters range perfectly acceptable for your parts? Or is plus or minus 0.0001 millimeters absolutely mandatory? If it's mandatory, non-negotiable, then the thermal stability and the mechanical control of the LS-WEDM basically become gatekeepers. You likely need it.
Okay, tolerance first. Makes sense.
Question 2, surface finish. Is an excellent smooth finish, let's say around Ray 0.65 micrometers, sufficient for your application's function and quality needs? Or is that mirror-like finish down around Ray 0.05 micrometers actually required by the print or the function? If that mirror finish is a genuine functional requirement, then the complex skim cut capability and that superior flushing of the submerged LS system become essential.
Got it. Tolerance finish. What's next?
Question 3, geometry. Are the parts you're making generally standard shapes? Or do they consistently require highly complex features? Things like extremely sharp internal corners, which are only accessible using that ultra-fine wire, or aggressive taper angles, maybe approaching that 45-degree mark. If complexity is king in your workload, then LS-WEM is often the only practical solution.
Okay. Tolerance, finish, geometry, and the final one must be the business side.
Exactly. Question 4, business model. Is your competitive advantage based on needing low operating costs and maybe higher cutting speeds, leveraging that economical reusable wire to compete effectively on volume or standard parts? Or does the extremely high value and potentially very low scrap rate of your ultra-precision parts fully justify paying that continuous premium for disposable wire and high-purity consumables? Can you price accordingly?
That really is the ultimate litmus test, isn't it?
It has to be.
Listening to this, It seems crystal clear that the MS-WEDM is really the default path to profitability for the vast majority of high-quality machining work. You only make that huge leap, that investment in LS-WEDM, when the application truly involves non-negotiable, mission-critical accuracy or features. Usually, as you said, reserved for those high-stakes industries like medical implants, deep-sea components, maybe very specific aerospace tooling.
Couldn't agree more. If you can meet the specification reliably with medium speed, you absolutely should. The cost differential, both upfront and ongoing, is just too massive to ignore otherwise.
Well, we certainly dissected the LS-WEDM secrets today, haven't we? From its absolutely crucial thermal management system to that fundamentally different disposable wire philosophy. And that leads us perfectly into our final provocative thought for you, the listener, to maybe chew on. Think about this. The MS-WEDM relies on that cheap reusable wire, but it accepts the inherent risks the wire wear, the potential path instability. Small risks, maybe, but risks nonetheless. Conversely, the LS-WEDM relies on expensive, single-use wire specifically to guarantee perfection, eliminating those risks. So in industries where the failure of a single tiny part may be component inside a pacemaker, or something critical in a satellite could cost millions or even lives, does the high continuous operating cost of the LS-WEDM a single-use wire actually stop being a burden and instead become, well, the cheapest, most effective insurance policy you can buy against catastrophic failure? Something to consider. Think about the true cost of failure as you apply this checklist to your next major investment decision. Thank you for diving deep with us today. We really hope this comprehensive guide helps you make the most informed and financially sound decision possible for your shop.